Okay, so now in this very handy format here, we can also take and make 3 times v. If vector v is 2i plus 3j, or 2 comma 3. And if I take 3 times the vector 2, 3, and then we're going to get the vector 3 times 2 is 6, 3 times 3 is 9. And that would be the same thing as 6i plus 9j. So this is A. For part B, we're going to take 2 times v, so we're going to take 2 times the vector 2i plus 3j. Notice I'm just using one or the other, just kind of whichever way you like. And then we're going to take and subtract 3 times w, which is defined as 3i minus 4j. Okay, so we're going to end up with 4i plus 6j minus 9i plus 12j. So we're going to combine the j pieces and the I pieces to form our final result. So that's going to be negative 5i. And then I got 6 and 12, so plus 18j. And we could also write that as negative 5, comma 18. It's a vector that results from twice v minus 3 times w. Now C here, we finally get to figure out a magnitude from some vector. So we're going to take the magnitude of the vector v, and if we look back at the definition, that said, well, that's the square root of the a part squared. So that's going to be 2 squared plus the b part squared, so 3 squared. It's the square root of 13. That's the magnitude of this vector v. Okay, we've got this little theorem that we're going to tap into. Remember how we said that the unit vector is going to have the same magnitude, but it could go off in any direction. The unit vector always has a magnitude of 1, so if we ask for the magnitude of the unit vector, it's going to come back 1. But we don't know anything about the direction. But if we have some vector v, and we wanted to create a unit vector in its direction, this is how we do it. So v is going to carry over the direction to us, but it's going to lose its old magnitude, and the u is going to be a vector in the direction of v, but it's the unit vector. The way we calculate that is we take the original vector v, divide it by its magnitude, and that's going to indicate the direction of v as a unit vector. Okay, there's a little proof down here. I'm going to, in the interest of time, we're going to move on. Okay, if we wanted to, we could capture back v. If I know that the unit vector in the direction of v is vector v over its magnitude, then of course if I multiplied both sides by the magnitude of vector v, I can see that this result holds, that vector v is its magnitude times the unit vector. All right, let's put these ideas to work here. So if I have a vector described here as v, or I can think of it as 4 comma negative 3, I know that the unit vector in its direction is given by the vector v divided by its magnitude. So let's go get the magnitude of v. Okay, that's just going to be the square root of the sum of its component parts, so 4 squared plus negative 3 squared. Okay, so that's going to be equal to square root of 25, which is handy. It's perfect square of 5. All right, so we've got the magnitude of v. It goes 5. And now we want to get the unit vector that goes the same direction as v. So we're going to take and write u is equal to v, which is 4i minus 3j over 5, because that's the magnitude of v. So the unit vector in the direction of v is going to be equal to 4/5 I minus 3/5 j, or if we want it in this format here, 4/5 comma negative 3/5. Okay, now if that's true, when I ask for the magnitude of our result here, if I ask for the magnitude of that vector, I should get back a 1. So let's check that out. So this would be 4/5 squared plus negative 3/5 squared. Alright, and then that would be 16/25 plus 9/25 square root of 16 and 9 is 25. And as we expect, we got a unit vector, so its magnitude is 1. Okay, and if we think about what we've been finding with that unit vector, we can think of it as a radius of the unit circle. So all of the directions are defined as points that land on the unit circle, and that means that the x component on the unit circle is the cosine of alpha, and the y component is the sine of alpha for the angle alpha that it makes with the x-axis here. So it allows us to think of a vector v as its magnitude times cosine alpha I plus sine alpha j. Okay, so this is what we call the direction angle at alpha, because it meets the unit circle at the point that we create when we find the unit vector from some vector v that has the direction from v. Okay, so this sets us up for some applications. So we've got two different kinds of vectors we're going to look at. One is representative of a velocity vector, which is going to represent magnitude and direction, and that would be like, so speed, the magnitude is represented by the speed, and then the direction is where you throw it or where it blasts off from, whatever. And another way that we'll look at this is the force acting on an object, another application, and we would refer to that as a force vector, but they're both going to be representative vectors that we've discussed in general so far. So let's take a look at an example here. So if we have a ball thrown with an initial speed of 25 miles per hour, and the direction that it makes an angle of 30 degrees with the x-axis, and so we want to create this velocity vector in terms of the I and j, and that's going to allow us to figure out what the initial speed in the horizontal direction is and the speed in the vertical direction is, because this overall speed of 25 miles per hour at a 30-degree clip is caused by some of that magnitude is going in the x direction and some in the y, and the combined result is this 25 miles per hour. Okay, so in this example, the ball is thrown at 25 miles per hour in a direction making 30 degrees with the positive x-axis. So kind of like this picture, and since we've got the magnitude, or we know that for this vector that's equal to 25, and we know that this angle here is 30 degrees. So let's substitute and create that vector. So v is equal to its magnitude times the cosine 30 degrees x direction, so for the I there, plus the sine 30 degrees So let's go ahead and get these values plugged in here. We're going to have 25 times, so remember our cosine of 30 degrees is going to be the square root of 3 over 2. And then our sine of 30 degrees is going to be 1/2. So the vector v breaks down to 25 times the square root of 3 over 2i plus 25 halves j. And this value here is the part of the force that's going in the direction of the x-axis, and this is the part going in the upward direction along the y-axis. So if we plug those into our calculators, and the units were all given to us in miles per hour, so that would be roughly equal to 21.65 of that force is devoted to the horizontal direction, and then 12.5 is pushing it upward, and the combined result is the 25 miles per hour at the direction that coincides with this 30-degree angle. Okay, so when we were talking about a velocity vector or a force vector, those are two applications of vectors, but we did indicate that the direction angle was the angle that was made with the positive x-axis, so we're interested in this angle. But we know that the point on the angle here is 4, -4, so if we think about the tangent of some angle, that would be y over x, or -4 over 4. So where is our tangent? -1. And if we do an inverse tangent for -1, -45 degrees. Okay, and we know that that's this angle here. That's our -45 degrees. So to rephrase that in terms of alpha here, we're just going to take the 360, subtract the 45. So we need alpha to be equal to 315 degrees.